So what we're going to do here today is we're going to do some specific heat capacity. And unfortunately for us, the symbol for specific heat capacity is an uppercase C, just like it is it could look like the symbol for concentration, or it could be the symbol for centimeters. Uh, but with a alphabet of 26 letters, you can only and so many different things that we might talk about in chemistry, you have to reuse some letters again and again. So naturally, this is called specific heat capacity because of the C. We're also going to talk about changes of state. And your book makes a great deal about heat, work, and internal energy, and I don't. So we're not going to talk much about that. We are going to talk about enthalpy changes. And when I say talk about these things, as little talking as possible just to get the idea under your skin, and then doing some problems that are associated with these things. And this is probably all we're going to get to today, although the next section would be calorimetry. And I haven't posted any videos on this yet, but I posted videos on these other things. For the calorimetry, I'll be posting videos today, and there'll be a demonstration of what we call constant volume calorimetry or bomb calorimetry. You're going to do a lab that uses constant pressure calorimetry. So you might want to look for a coffee cup because that's what you're going to need. And then we finish off with basically Hess's law. And these are the areas where I really like what's going on. And I should say there's one more thing called standard enthalpies of formation. So this is what we're going to be doing on Friday, and this is going to be today. And we'll go ahead and get going. So just a very short background on specific heat capacity. C, this is the amount of energy, heat energy, required to heat 1 gram of a substance by 1 degree Celsius. Now, for heat energy, we use the symbol Q. And this also could be considered to be 1K because a change of 1 degree Celsius is the same as a change of 1 Kelvin. They're the same change. And here we're talking about changing the temperature. So this might be going from 13 degrees Celsius to 14 degrees Celsius, which is a change of 1 degree Celsius. Now, if we look at that in terms of K, that would be 286 degree or K to 287 K, which is a change in 1K. So here the definition is a little flexible because of the size of a degree Celsius is the same as the size of a K, how big they are, not the actual numbers. 1K does not equal 1 degree Celsius. Okay, so the specific heat capacity is a physical property. And oftentimes it's used to identify a substance. And there is one specific heat capacity that you should measure for one substance. It's the specific heat capacity of water. So the specific heat capacity also depends on the state. That is to say, the specific heat capacity of ice is different than the specific heat capacity of water. And the specific heat capacity of steam is different than the specific heat capacity of water. So I'm going to actually write that down. They're not the same, even though these are all H2O. Now, this is the one you should memorize. The specific heat capacity of water is 1 calorie per 1 gram per degree Celsius, which is the same as saying 1 calorie per 1 gram per 1 Kelvin. Now, normally in the denominator, we don't write numbers. So this would be written 1 calorie per gram per degree Celsius, or 1 calorie per gram per K. So notice this is a very complex unit in that there's energy in the top, mass in the bottom, and temperature in the bottom. Now, if we talk about this in joules, which is what the book normally does, this would be 4.184 joules per 1 gram per K, or degree Celsius. I normally like to use degree Celsius, not K. Your book likes to use K. Okay, and the reason this works is because 1 calorie is 4.184 joules. Now, this is exact. This has 4 zig figs. And the reason this has 4 zig figs is because there are not exactly 4.184 joules per 1 calorie. It's a pretty good estimate. It's got 4 significant figures. Okay, so you should memorize that one. Now, if we look at the idea for the specific heat capacity of water again, 1 calorie per gram per degree Celsius, this actually tells us how to calculate specific heat capacity of a substance. What you will need to calculate the specific heat capacity of the substance is you'll need to know how much energy it absorbs or gives off. So that's Q. You will need its mass. So that's M. And you will need the change in temp. So this is the formula for specific heat capacity of a substance, where Q is equal to heat, energy. M is equal to the mass. And delta T is the change in temp. Now we have a specific way of writing out the change in temp. And it is this way. It's the temperature final minus the temperature initial. And it's always final minus initial, never the other way around. So it turns out that your change in temp can be positive or it can be negative. If you go from 0 degrees Celsius to 1 degree Celsius, that's an increase. 1 minus 0 is 1. But if you start at, let's say, 10 degrees Celsius and drop down to 0, your final is 0, your initial is 10, 0 minus 10 is negative 10. Your change is negative 10. So the change in temperature has direction associated with it. A positive delta T means you're increasing in temp. A negative delta T means you're decreasing in temp. Okay, so this is a formula you kind of want to remember. And a lot of people write it this way instead. Q is equal to Cm delta T. Now, I think your book uses an uppercase T for temperature, but that's irrelevant. Now, the reason people like to remember it this way is because everything's in the numerator on the left and everything's in the numerator on the right. And that's fine, but these are indeed the same equations. Okay, so let's take a look at a problem here from the book. So we're going to focus on this very first problem. I'm going to give you a chance to read it, and then we'll solve it. Okay, so we want to take this 1.74 joules per gram K, and we want to turn that into joules per mole K. So you can see that the energy unit does not change. The mass unit changes into moles, and the temperature unit stays as K. So we've got to change grams into moles. So how do we change grams into moles? And the answer is we need the molar mass. So we need the molar mass of benzene. So we have 6 carbons. Plus we have, this is supposed to be times. Maybe I'll put parentheses around that so it looks a little better. And we have 6 hydrogens. And when we total that, we get what? Well, let me multiply first. I'm not good at doing all these things in my head. So 72.06 grams and 6.06 grams for a total of 78.12 grams. Okay, so here we're going to take our 1.74 joules per gram K, and we're going to multiply by 78.12 grams per 1 mole. Now, I'm not using the label of C6H6 because we're only talking about benzene here. We're not talking about 2 different molecules. Now, when we multiply these 2 together, you can see clearly that's almost 2, and that's about 80. So 2 times 80 is 160. But clearly that's not 2 and that's not 80. So the answer's got to be less than 160. And in fact, it might be more like, 140. But let's take a look and find out. I think this is actually one that I did in the lecture that I posted. Now, we're going to be allowed 3 significant figures because of this 1.74. And we get 136 joules per mole K. Now, you might be wondering, what does that dot mean between the mole and the K? It means times. Okay, so if you're okay with this solution, give me a thumbs up. Okay, well, let's do the next one. So let me move my paper up. So here's the next question. How much energy as heat is required to raise the temperature of 50 milliliters of water from 25.52 degrees Celsius to 28.75 degrees Celsius? So we're given that the density of water is 0.997 grams per milliliter. So here we want to use this Q equals CM delta T for this problem because they're asking for energy. Now we know that the specific heat capacity of water is 1 calorie per gram per degree Celsius. Remember that K and the degree Celsius are interchangeable. We know that the mass of the water can be found because we have the milliliters in the density. So the mass is going to be 0.997 grams per milliliter times this 50 milliliters. And you can see that the answer is going to be really close to 50. And this is another one I think I've done in the lecture. So we get 49.85 grams. And we would round this to that 8 and call it 49.9. I'm just not going to round it yet. This has an infinity zig figs. Now for the change in temp, we've got 28.75 degrees Celsius minus 25.52 degrees Celsius. And this is where most students make their mistakes. And I'm going to show you what I mean by mistake. So the difference here is going to be 3. 5 minus 2 is 3. 7 minus 5 is 2. 8 minus 5 is 3. So we get 3.32 degrees Celsius. The mistake that people make is they look at this and they see 4 zig figs, and here there's only 3 zig figs. Why did we lose a significant figure? And the answer is, it's because we used to have a 2 in the 10 spot here and a 2 in the 10 spot here, but now we have a 0 in the 10 spot, and zeros don't count when they're to the left. Okay, so now we're set to get this done. I usually like to put parentheses around each portion of this. And you can see that the grams cancel, the degrees Celsius cancel, and the calories don't. So our answer is going to be in calories. And roughly we have 50 times 3.23, which is a little bit more than 150. In fact, you would say that 23 is about 1/4 of 1. So an additional 1/4 of 50 would be about 12. So the answer should be 150 plus 12, or about 162. And we only get 3 zig figs because of this and because of this. And so we get 161 calories. If you're okay with the solution, give me an okay. You okay with that, Jackie? Now, let me circle for you the things I'd expect to see on an exam. I'd expect to see that calculation. I wouldn't expect to see this calculation. I'd just expect to see the temperature. I'd expect to see this calculation. And here you'll notice that if you'd used 4.184, you would have gotten a different answer, but also a different unit, and that would be fine. Okay, let's put that off to the side. Now, this is a much tougher one. This is more of what's called calorimetry, if you will, but we don't need to know that idea to be able to do this problem. So I'm going to give you a moment to read this, and then we'll discuss how to do it. Okay, so for me, it always helps to draw a picture of what's going on with these situations and to think about it. So here I'm going to draw 108 grams of water, and it's got a temperature of 22.5 degrees Celsius. And to this, we're going to add 65.1 grams of water. So same size cup. That means the 61 is not going to be quite as tall. And we don't know what the initial temperature is. And so I'm going to write T initial here, and I'm going to write mass, mass, and T initial. Now, when they're done, I'm going to have to increase the size of my cups here. We have 108 grams of H2O at 47.9 degrees Celsius. And we also have 65 0.1 grams of H2O at 47.9 degrees Celsius. And you might be asking yourself, well, why is he drawing them separately when they're actually combined together? And the answer is because it's going to help me to figure out what's going on. Okay? So the first thing I'm going to say is that if this temperature increases to 47.9 degrees Celsius, this initial temperature must be pretty darn hot to cause this to increase to that temperature. And this initial temperature has to be above 47.9 because when you mix it with this cold water, this temperature is going to decrease. So I know the answer has to be greater than 47.9. Okay, so that's the first thing I'm going to do. I'm not even going to do a calculation. I just know my answer has to be greater than 47.9 degrees Celsius. Now I'm going to look at this here and I'm going to see that the mass is 108 grams. The change in temp is 47.9 minus 22.5. So 9 minus 5 is 4. 7 minus 2 is 5. And 4 minus 2 is 2. So that's our change in temp. And we know that the specific heat capacity for water is 1 calorie per gram degree Celsius. So what I want to do now is I want to take this information and I want to calculate Q for this particular situation. So I'm going to do that below down here, and we're going to lose sight of the problem. But I'm going to get Q is equal to Cm delta T, which is 1 calorie per gram degree Celsius, times 108 grams, times 25.4 degrees Celsius. Okay, so when I multiply these together, basically I'm multiplying 100 times 25, so I should get 2,500, but clearly a little bit more because that's 108 and that's 25.4, more than 100 and more than 25.4. But nonetheless, should be around 2,500, thereabouts, a little more. So 108 and my calculator said 259, which means I did something wrong. So I said it'd be around 2,500, but more. We get 2,743.2 calories. And this has 3 zig figs. This has 3 zig figs. So this is good to the 274. So we would write, if this were the final answer, which it's not, we would write this for the answer, 3 significant figures. Now, what do we know about this guy? We know that the mass is 65.1 grams. We know that the change in temp is equal to 47.9 degrees Celsius minus the initial temp. And what do we know about the specific heat capacity? Well, the specific heat capacity is 1 calorie per gram degree Celsius. But what do we know about Q? Well, here we know that this increases in temp by 25 degrees Celsius. So I'm going to make sure we understand that's plus. That makes this an endothermic reaction. Heat was added to this 108 grams of water. Well, this guy we know has to start at a higher temp than 47.9, and it drops to 47.9. What happens with the heat from that hot water? And I'm actually going to write cold and hot here for these waters. And then here we'll put warm. Well, the answer to me is obvious. All of the energy to warm up this water has to come from here. So heat is leaving the hot water, which makes it exothermic. So that means Q is minus 2,743.2 calories. So I'm going to go over that again. Because this cold water is absorbing 2,740 calories and warming to 47.9 degrees Celsius, the heat has to come from somewhere. It's coming from here. So that means 2,743.2 calories has to be leaving the hot water, which is exothermic, and exothermic means it gets a negative value. So give me a thumbs up if you understand why I gave that a negative value. Give me a thumbs down if you don't. Give me some sign you're alive. Okay. So here we actually have a way to calculate delta T. We can still start with this. Q is equal to C M delta T. I'm going to change that to Q is equal to C M T final minus T initial. And then Q is equal to C M T final minus C M. Actually, I'm going to do this. Q over CM is T final minus T initial. And then I'm going to jump ahead and say that T initial is equal to Q, is equal to T final minus Q over CM. Let me think about that. Did I do that right? Yep. So here's the formula I need to use, and I've run out of space. So I'm going to take this and I'm going to put the answer right here. So T initial is going to be T final, which is 47.9 degrees Celsius, minus negative 2,743.2 calories over 1 calorie per gram degrees Celsius, and a mass of 65.1 grams. So we get 47.9 degrees Celsius minus, so I'm going to take my 2,743.2, divide it by 1, and then divide by 65.1. And here I have to remember that all of this is going to be negative, but then when I take the negative of a negative, I get a positive. So I end up having positive 42.1 degrees Celsius. I'm going to go ahead and round to 3 zig figs because of the 65.1 and because this has 3 zig figs. When we add these together, we get 90. My calculator simply puts out the number 90, and that would be wrong. This is good to the 10th, and this is good to the 10th. So that means we need to have a number here in the 10th, and that number is 0. And there's your initial temp. Now, remember, we predicted that this has to be much hotter than 47.9 for it to warm this cold water up to this warm temperature. And it ends up being quite a bit warmer than 47.9. So, does everyone understand the solution here? If you do, give me a thumbs up. Do you understand why I kept the two waters separate in the problem so that it made it easier for me to figure out what was going on? So do you understand that part also? Yeah, to do this problem, where we combine this and just make one drawing that has water in it at 47.9, it would not have helped us to do the problem. It would have been a little more brain work, and my brain isn't that good. All right, let's take a look at another problem then. So we're going to switch gears now, and we're going to look at something called changes of state. So when we talk about changes of state, we're talking about changes of state for a pure substance. There's no chemical reaction here. It's just something like ice melting or water boiling, or it could be gold boiling. It's just a change of state, but the substance does not change into another substance. Now, if we take a look at a energy diagram for changes of state, they all look like this, where this is energy and this is the temp. So here we're starting off with a solid, and this is cold temp and this is hot temp. So it turns out that solids can be below their melting point. You can have ice that's colder than 0 degrees Celsius. And when you add energy to the solid, it warms it up. Now, when you get to what's called the melting point of the solid melts, but notice that the temperature doesn't change. And this is because here, I'm going to call this 1. 1, you have the solid heating. 2, you have the solid melting. So that means you have solid plus liquid together. And if these two things are in thermal contact, they're in thermal equilibrium, which means their temperature does not change. And here, you can't have a solid be higher than its melting point. It's not a solid anymore, it's a liquid. So here in this number 2, this is when you have the solid melting, and this is a phase change or a state change. Now, what happens when all of the solid melts and now you only have the liquid? Well, at this point in time, the liquid can change temp. It can warm. So this could be ice warming, then ice melting, then water warming. So now we're about to boil your pot of water. And then when the pot of water gets to be a certain temperature, it starts boiling. And the temperature of the boiling water is constant. It doesn't change. And the temperature of the steam that it makes also doesn't change. So here, we'll call this 4 and call this 3. 3, we have the liquid warming or heating. And 4, we have the vaporization, we'll call it. And this is a state change. And notice whenever you have a flat part of the curve or graph, there's no change in temp. The temp is constant. And then finally, when all of the water has boiled off and you've made steam, the steam can then increase in temperature. So 5, we have steam heating. So how do we calculate energy changes for these things? Well, we need to talk about 2 and 4. For 2, you use something called heat of fusion. And heat of fusion is going to have the units of energy over mass. So typically you get joules per gram. So if you want to use heat of fusion to calculate the change in energy, you can see that the formula is Q is equal to your heat to fusion times mass. So we can write something like this: Q is equal to heat F times mass. And mass times heat of fusion, the grams should cancel and you get joules. Now for number 4, we don't call that heat of fusion. We call that heat of vaporization. And that's equal to energy over mass also. Now, go ahead.
What does number 3 say?
Liquid heating.
Oh, okay.
The W shouldn't really be there. Okay. So you basically have 2 formulas for calculating energy changes in this diagram. One formula is this: Q equals Cm delta T. And the other one is Q is equal to heat times mass. So when do you use Q equals heat times mass? And the answer is when the change in temp is 0. And when do you use C equals M delta T? That's when the change in temp is not equal to 0. And that's how you know which formula to use. If there's a change in temp, use the change in temp formula. If there's no change in temp, then use the heat mass formula. Let's take a look at this applied to a problem, okay? So here's the problem. Changes of state. I'm going to move the paper up to give myself a little more room to work. The energy required to melt 1 gram of ice at 0 degrees Celsius is 333 joules. So that first sentence is saying that it's 333 joules per 1.00 grams, which is 333 joules per gram. So that is the heat to fusion. And I know it's heat of fusion, not heat of vaporization, because we're talking about melting. If 1 ice cube has a mass of 62 grams and a tray contains 16 ice cubes, what quantity of energy is required to melt the tray of ice cubes to form water at 0 degrees Celsius? So we're talking about ice that is at 0 degrees Celsius, and we're going to melt it and make water at 0 degrees Celsius. So here, the ice is at 0 degrees Celsius. The water will be at 0 degrees Celsius. So there is no change in temp. And another way to say that is the change in temp is equal to 0. Whoops. Change in temp is equal to 0. So that means for this calculation, I want to use Q is equal to heat times mass. So how do I get the mass of 16 cubes? Well, for the mass, I'm going to take 16 cubes times 62.0 grams per cube, and we're going to get the mass. So let's see what we get. 10 times 62 is 620. 6 times 62 is around 360. So 360 plus 620 puts us close to 900, right? No, 1,000. So the answer should be close to 1,000. How many significant figures are we allowed in this answer? Who wants to take a stab at that?
Would it be 2?
That's a good guess. It's either 2 or 3, right?
Yeah.
Okay. And the answer is depends. How well could you count 16 cubes? Could you do it exactly and get 16 and there's no doubt that it's 16? It couldn't be 15, it couldn't be 14. Is that a number you could do?
Yeah.
Okay, so that means it's exactly 16, which means 16.000000 cubes, which means infinite zig figs. So here's a thing that we always want to remember, that when we have amounts where we're counting things, you have to ask yourself, is this something you could really count? Now, what if this were 1,600 cubes? Is that something that you'd be able to get away with? Could you open up, let's see, that would be 1,600 would be 100 ice cube trays, and make sure you get all the ice cubes into your bucket that you're collecting without losing any off to the side. Is that something that you could probably do? I don't know. So if this were 1,600, I don't think it would be exact. So we actually get 3 zig figs because of the 62.0. Okay, so that's the mass. So now to calculate the heat, we take our 333 joules per gram, multiplied by the 992 grams. And here you can see the grams cancel out. So we're going to be left with basically 1,000 times 333, which makes this 333,000. A little less because this is not quite 1,000. And I get 330,336 joules. Now, how do we write this answer out so that we have 3 significant figures, 3 here and 3 here? Well, what do you think of this? Would that be the correct answer? Yes or no?
No.
No is correct. How many significant figures does this have? 2. So what if we did this? Well, what could we do? And the answer is simply this. Let's see, I moved the decimal over 1, 2, 3, 4, 5 times. So do I want that 5 to be a positive or a negative? And the answer is I want it to be a positive because this initial number is bigger than 1. And oops, I got to get rid of that 0. So now we have 3 significant figures. And because I don't like this, I'm going to rewrite it. And there's your answer. And so you see, if I had done this in a lab notebook and I crossed that 0 out and rewrite this way, everyone can see why I crossed that 0 out. I realized, oops, that's too many significant figures. Any questions on this one, or are we okay? If we're okay, give me a thumbs up. Okay, great. Let's take a look at another problem. So this one's a little more complicated. What quantity of energy in joules is released to the surrounding if 1 milliliter of mercury that has a freezing point of minus 38.8 degrees Celsius is cooled from 23, that's about room temp, to its freezing point, minus 38.8, and then frozen to a solid? So we have 2 things going on here, and we need to account for that. So here's how we account for that. We've got our liquid mercury. The wavy stuff at the top is supposed to signify a liquid, but I'm going to put L here. And this is at 23.0 degrees Celsius. We're going to cool it. And here, it's still mercury, and it's a liquid, and it's at minus 38.8 degrees Celsius. And then we're going to freeze it. And so here I'm going to write mercury solid. And what is the temperature when we're done freezing it? It's still minus 38.8 degrees Celsius. So you can see here we have a change in temp, and here the change in temp is equal to 0. And here the change in temp is going to be, we need to think about this. Look at this change in temp. So we go from 23 down to 0 plus negative 38.8. It's going to be around 60 degrees temperature change. Now this temperature change is going to be negative 61.8 degrees Celsius. Now, I did that in my head and with a calculator, but you could do this by doing this. And in this case, the final temp is negative 38.8 degrees Celsius. The initial is 23. And you can see that this is going to return a value that's negative. Okay. So that means that for this part of the heat change, I want to use Q equals Cm delta T. And here I want to use Q is equal to heat times mass. So I figured out for the two different parts that are happening, what type of equation I want to use. Are we okay with what we're doing here so far? If we are, give me a thumbs up. Okay, well, let's take a look at this part here where we're cooling. We've got 1 milliliter of mercury, and we're going to cool it. But I think we need to turn that into grams of mercury, and then we can calculate. It looks like we can calculate joules of heat. Okay. So I'm going to separate this into two problems. I'm going to convert milliliters to grams. So I got 1.00 milliliters times 13.6 grams per milliliter, which is 13.6 grams of mercury. And then I'm going to use this formula here. Q is equal to Cm delta T. And you'll notice that when I'm solving these problems, I write the formula that I'm going to use, and then I put the numbers in. I don't just straight away put the numbers in. And the reason I do that is because it's easier for a person to see what I'm doing. So here, the specific heat capacity of mercury is this 0.140 joules per gram. And I'm going to put degrees Celsius. Remember, K and degrees Celsius are interchangeable. And now that I have that number written down, I'm going to move this up. The mass is 13.6 grams. And the change in temp was minus 61.8 degrees. Now, I want you to take a look at what I've done so far. Well, actually, let's solve this. Now, we can tell, since only one of these numbers has a negative value, and we're multiplying them all together, the Q is negative. So that means this is giving off heat, or it's releasing heat. So 0.140 times 13.6. And this is a little more than 1/10 and then a little less than 0.2. So I know that this answer should be between 1.36 and say 27, or 1.36 and 2.7. So I think probably this times this is around 2. And 2 times that should be around negative 120 something. So let's see what we get. And we get negative 118 joules. So that's the heat change for this first part. And the minus 118 means that energy is being released. And I know this is a tough nut for us to crack. You know, how is it that energy is being released here? You don't really see it, or it's hard to envision. And I have a really tough time with that. But when I think about the opposite, if I start at 38.8 and I add positive 118 joules, that is going to make this warmer. So if I start out at a cold temp and I add endothermic energy, that'll make this warmer. So when I think about that and I think about the law of the conservation of energy, that means when I reverse it and I go from hot to cold, the energy has to be negative and it has to be released. Okay, so this is the first part. And then the second part, we use Q equals mass times heat, or heat times mass. And here we're given that the heat of fusion is 11.4 joules per gram. So for this second part, I can actually do that up here, 11.4 joules per gram times 13.6 grams. And you can see we're going to get a value that's greater than 136 by a little bit, so maybe 150. And it's 155 joules. So even here, you can see that I have a formula that I'm following. So take a look at this down here. You can see first I take the milliliters and get grams, and then I calculate the heat. So here, you can see what's going on here. Now imagine I didn't have that and I just had Q is equal to, and I plug the numbers in. Is it as obvious what I am doing compared to writing the formula down? Which one do you think is better? So do you think putting this in is better for people to see what's going on or not? Is it better? Yes or not better? No. Okay. So you see why I do it for you each time. It's because I want you to be able to see what's going on. So on an exam, I like to see that stuff. Okay. Let me put that off to the side. So we're done with that problem. And we're going to do one more problem here. And this is an enthalpy change problem. So I need to talk about enthalpy very quickly. Enthalpy has the symbol H, and we calculate changes in enthalpy. And changes of enthalpy are basically equal to Q when you have constant pressure. So for instance, any chemical reactions that you do in a room are at constant pressure. The pressure of the room is not changing appreciably. if you do a reaction inside of a closed container where the pressure can change, then this would not be constant pressure. So basically, all of the chemical reactions we do are at constant pressure as long as we're not really producing any gas. So do you remember the reaction where we made a precipitate? No gas was formed? That's constant pressure. All right. So delta H is the heat change when you have constant pressure. Now, when you write down the change in enthalpy for a reaction, this is how you would do it. So this is an example right here from our book for this problem. So I'm going to write calcium oxide solid plus 3 carbon solid is equal to calcium carbide solid plus carbon monoxide gas, and the enthalpy change is positive 464.8 kilojoules per mole. Okay. This is an endothermic reaction, and it's endothermic because delta H is positive. What type of reaction would this be if it were exothermic? And the answer is that would be negative. Now, if we have to add heat to make this happen, we could also write it this way. So when the delta H is positive, the heat is really a reactant. Another thing I want to point out to you here is that we can write this reaction backwards. So you see, I've taken the products and made them reactants. That means I take the reactants and make them products. So here you can see if we reverse this reaction, we actually get heat as a product. And in this case, when heat is a product, it's being released. And when it's being released, that's exothermic. So this will be minus 464.8 kilojoules. So again, how do I know this is negative? And the answer is because the heat is released, it's emitted, it's exiting, it's exothermic. So what students sometimes have a problem with is, if that's negative here, why don't you put negative up here? And the answer is, the only reason we put a negative here is so people know it's a product. That's the only reason we put the negative there. Otherwise, we just put 464.8 kilojoules. So the real question shouldn't be, why don't we put a negative here? It's, why do we put a negative here? So what is the answer to why we put a negative here? So we know heat is a product. And if heat is a product, we call it exothermic. And it's negative. By definition, there is no such thing as negative energy. So I don't care how many times you go to see Madame Clairvoyant, there is no negative energy. All right, so that's a little bit about delta H. So let's take a look at this here and answer this first question for me. Endothermic or exothermic? If you think it's endothermic, pick go slower. If you think it's exothermic, pick go faster. If you think it's endothermic, pick go slower. Exothermic, pick go faster. Got to pick, Jackie. Okay, and you're both correct. It's endothermic because it's positive. That's it. What is the enthalpy change if 10 grams of calcium oxide is allowed to react with an excess of carbon? So here I'm going to move this on up and get out a fresh piece of paper here. And to calculate the energy change, this is what we do. We're going to start off with 10 grams of calcium oxide. We're going to turn that into moles of calcium oxide, and then we can turn that into energy. And I know I can turn this into energy once I get moles, because here, this is moles and energy. So all I need is the molar mass of calcium oxide. Oxygen is 16. Calcium is 40.08. So that's 60.08 grams per 1 mole. Now you'll notice now I'm using labels here, whereas before I wasn't. The reason I'm using labels now is because we have 4 different things up here, not 1, 4. Okay, now I can multiply times plus 464.8 kilojoules per mole of calcium oxide. And let's see what we get for the answer. So can everyone see that 56 will go into 464 about 8 times? And I did that quickly because I know that 56 goes into 560 10 times. So it seems like it'd be about 2 times less. So if this goes into that 8 times that is 80. So the answer should be around 80. And we get 82.9 kilojoules. So that's the answer for what is the enthalpy change if 10 grams of calcium oxide is allowed to react with an excess of carbon. So I'm going to change the question. What is the energy change for 10 grams of carbon with excess calcium oxide? So here we're going to start with 10 grams of carbon, turn that into moles of carbon, and then turn that into energy. So let me show you how this differs a little than what we have above. So we're going to start with 10 grams of carbon times 1 mole of carbon per 12.01 grams of carbon. And here we're going to have 464.8 kilojoules. It's still positive. But here, what do we put for moles of carbon? And the answer is, in the balanced reaction, do you see that it says 3 here? That's 3 moles of carbon. So here I had per 1 mole of calcium oxide. Why per 1 mole? Because the coefficient was 1. So this is a little tricky. When they say per mole of reaction, they mean use the coefficient of whatever it is you're interested in. Now I'm going to move this up just a little bit so you can see what I've written there. And we want to estimate the answer. 10 divided by 12 is 1. So 464 divided by 3 is 150. So the answer is around 150, a little less. 10 times 464.8 divided by 12.01 and divided by 3. And we get 129 kilojoules. Okay, so I'm going to ask you a quick question. Do you understand why I used 3 here and why I used 1 here in these calculations? If you do, give me a thumbs up. So here, this is what they mean when they say 464.8 kilojoules per mole of reaction. They mean use the coefficient for whatever it is you're interested in. And the last thing I want to do, which is a prelude for Hess's law and all of that stuff, is we want to draw what's called an energy level diagram for this reaction. And the reason I want to introduce this to you today is because it's really a complicated type of issue. It's a different way of thinking. And the longer you have to think about it, the better you're going to be at it. So for an energy level diagram, basically you write the reaction vertically. So if you have A turning into B, you might write it this way. So this shows A turning into B, or it might be this way. So do you see that this has the same feel as this, in that we have A, the arrow points to B. Here we have A, and the arrow points to B. And here we have A, and the arrow points to B. So which of these two is correct? And the answer is it depends on the type of reaction. In this reaction, this is endothermic. This says that you have to put energy into A to turn it into B. This one is exothermic because you have to release energy to take A and turn it into B. So do you understand the directions of the arrows in endo and exo? And here, I really think this makes sense because exo is plus, and when I'm adding energy to A, I go higher, and when I'm taking it away, I go lower. So this is one of the reasons why they chose endo as plus and exo as minus. So if we take a look at this, I'm going to show you step by step how to turn that into an energy level diagram. Your first step is that this reaction is endothermic. Your second step is to draw an arrow going up because it's endothermic. Your third step is when you draw that arrow, you want to draw a line at the bottom and a line at the top. And your fourth step is you always want to put at the head of the arrow the products, and at the bottom of the arrow, the reactants. And when I say the head of the arrow, I mean the pointy part. So if the pointy part is down, you put the products on the lower part. So do you understand the steps I've outlined so far? Endothermic means arrow down, up, sorry. Once you draw the arrow, you draw a line on the bottom of the arrow and the top of the arrow. And really, I should say at the pointy part versus the other part. And the products always go next to the side of the arrow that is down. If, and this reaction isn't this way, if it were exothermic, you would start with an arrow down, and then you would draw two lines, one on either side of the arrow. And the way you would fill it in would be that the reactants would go here and the products here. So do you understand here, the products always go at the pointy part of the arrow? And the other thing that we're doing here is we always write on top of the line, not beneath it. So for this reaction, It is endothermic. Now, what I want you to do is I want you to try and do the rest of this, but instead of writing the word reactant and product, actually write the reactants in and actually write the products in for this reaction and give me a yes when you're done. And I'm going to pause the recording for just a moment here. So you have your answers. That's great. So let me show you what we would do. Because it's endothermic, I'm going to draw an arrow going up. And here, I'm drawing the arrow longer just because I have more room to work. I'm not showing you instructions here. I draw a line at the bottom and one at the top. And here at this side of the arrow, I want to put the products, which are calcium carbide plus carbon monoxide. And on the other side of the arrow, I'm going to put the reactants, which is calcium oxide. And so, how did you guys do? Did you draw something similar to that? If you did, give me a thumbs up. Okay, now there's only one way we can make this better. And that's this. We can actually attach the energy and put it into the energy diagram. So 5, add the energy. Okay, so do you understand this part here? If you do, give me a thumbs up. Last, before we leave, if I draw this arrow in, what would you write down for the energy? Give it a shot. When you think you have the right answer, give me a thumbs up. And actually, rather than say when you think you have the right answer, when you have an answer, give me a thumbs up. Okay, and the answer would be and the reason it's negative is because the arrow's going down. The reason is 464.8 because it's the same reaction backwards. How do you guys do? Did you do okay with the negative 464? Excellent. All right, turn your mics on, say goodbye.
Bye.
Bye, everyone.
We'll see you on Friday.
See you then.
Or before then, if you come to pick up your kit tomorrow.
Oh, yeah. All right,
Just
bye,
give me-
guys.
Give me a time so I know when you're going to come. All right, bye-bye.
Yep.